Our next speaker is our very own YSarazin.
So I think I should start by thanking the organizers for the kind invitation. There's going to be something about turbulence, boundary, and also avalanches at the end. Oh, it's not shared. Oh, and layers as well. Well, those are the authors, but really most of the work was done by Olivier Panicaud, a former PhD student who defended end of last year, whom we co-supervised with Pascal and Ken here on the experimental side. So let's start by context and motivation. So confinement in tokamak plasma is really desirable because it improves the performances. And we know from experimental measurements that the plasma can bifurcate towards what we call improved confinement regimes. One famous example here comes from the H mode discovered in Aztecs at tokamak in Germany in early 80s, where you can see here for the temperature and the density, electron temperature and density, the core plasma would be here, and you go towards the edge here. And what you can see in the low confinement regime, so-called L mode, there is no steep gradient close to the outside region, while when you bifurcate towards the NH mode, there's a pedestal that forms, so a steep gradient, and the same can occur on density as well. So there's has been a lot of work, experimental and theoretical, to try to understand this bifurcation. So far, there's no really first principle prediction, but at least we know a few things about this bifurcation. And two things to keep in mind are, first, the fact that when the plasma bifurcates toward this regime, then there's a strong reduction. This is versus time, by the way, that's for the radius. So versus time, when you measure turbulence in this region here, then it drops suddenly to a low level when you try bifurcate from L to H mode. And this is associated with an increase of the mean flow of the plasma. The plasma starts radiating at a higher speed in the H mode. So we think that there's more than a correlation. There's a causality, some causality here, which still needs being really pinpointed. But one of the points that I would like to emphasize on during this talk is the fact that turbulence can self-generated flows that actually can have been suspected and measured as well experimentally to play a key role in this transition. Yet those flows are difficult to measure experimentally. They can develop small scales. One famous example here was published recently based on jet measurements. Jet was the largest tokamak in the UK, where you can see close to the region of the transport barrier develops those oscillations here in space that are reminiscent of what we can expect from well-structured flows generated by turbulence. But this was one example just prior to the bifurcation. But most of the time, you do not see them. This is one example here. Although experimentally, the accuracy would allow you to measure those. So they are kind of elusive. And we know from numerical simulation that those structured flows, zonal flows, happen in a certain parameter range, and especially one seems to be critical, which is the distance to marginality. You can see it as a nonlinear threshold for turbulence, and here is one example. That would be the marginal region in terms of the temperature gradient, and when you move farther away, then there's a region where you observe the buildup of those structured flows called staircases. So all in all, we wanted, in the framework of this PhD thesis, to provide some understanding of the parameter regime where we could expect such structured flows to guide a bit the experimental measurements close to the transition from L to H mode. So the idea was to develop or to use a minimal model able to address the huge parameter range that would contain the basic features, at least that we need. It should be given to solve both the equilibrium and fluctuating components, look at the steady state so that the flows have time to develop and to self-organize. Okay. So this comes to the outline. So I will present the model here, introducing first the two main instabilities that we think are relevant for the edge plasma, collisional drift wave and interchange, which is reminiscence of Bénard. Then come to the model itself, and then look at the main results. So the first instability is collisional drift wave. So the direction of the confinement is horizontal here. Y is one of the periodic directions here. And so consider a wave of the electric potential here in blue that defines region of positive and negative values. And imagine that you have a wave also of density here that is shifted with respect to the potential perturbation. Because of this potential perturbation, then you have an electric field that will develop in between those bands here. And the electric field will trigger an E cross B flow, which goes in opposite direction depending on the region you look at. And then what this E cross B flow will do to the matter, to the particles, is to affect that part here to the left and that part to the right. And you see that there's an imbalance here that leads actually to amplify the perturbation. So this is the essence of the instability. You need a density gradient and a phase shift between the two. The other instability, the interchange or Bénard-like, comes from the fact that you have a kind of effective gravity in the tokamak. You can see the force, part of the force is the centrifugal force due to the fact that the magnetic field decays like 1 over the major radius. So the grad B always points towards the symmetry axis here, but the pressure gradient goes toward the core, the hot core. So you have an unstable region, a stable region here, and the two are coupled through the magnetic field lines. So all in all, in the model that we're gonna look at, we have two control parameters. The collisional drift waves happen with a control parameter which accounts for the parallel conductivity in the plasma, plus the wavelength along the magnetic field lines, and it scales as presented here. So it depends on temperature and inversely proportional to the density. For the effective gravity, then you have a different scaling with respect to temperature. You see also the major radius that appear here. So you may expect, because of this different dependency, to observe different kind of instability depending on the plasma you look at and the parameters. Looking at the linear properties of those instabilities, so scanning the C parameter, this is in log scale, the same for the G parameters for the interchange or Bénard-like. You see that in the region where Bénard is most active, then the growth rate is fairly large, and it becomes very small, close to this boundary, and this region is stable here. Another parameter which is of interest is actually the linearly what you can expect in terms of the phase shift between the two fluctuations of the density fluctuations and electric perturbation. The reason being that the overall flux that you can expect scales like the magnitude of the fluctuations, but also the sign of their phase difference. And the interchange tend to maximize this phase difference. So at a given level of perturbation, then you expect a large flux, and it's the opposite for the drift wave. So slightly less dramatic in terms of transport for a given level of perturbation. So the model, we start with a three-dimensional model, which is actually, that was proposed by Hasegawa Katani. You heard about it a few times already in this festival. this is the very start, with the sigma parallel being the parallel conductivity, to which we add some additional features. The first one is the homogeneity of the magnetic field, as Wakatani considered a straight field lines. And this new feature adds two terms here, proportional to G, which is the effective gravity, if you wish. So the analogy with neutral fluids, or TFT, the electric potential would be the stream function in an incompressible fluid. Drift waves amount to Rossby waves. In homogeneity of B, the effective gravity, as I said, and the interchange is very Bénard-like. The additional feature we accounted for is it's isothermal, but we took into account a finite temperature for the ion. So tau is just the ratio between ion and electron temperature. And you see that the change is quite substantial, because you move from a vorticity, which is just the Laplacian of phi, and then you have another piece here that accounts for what we call the diamagnetic velocity. So to go from the 3D to 1D, actually, we keep only the direction of the confinement, or the radial direction across the magnetic flux surfaces. And we keep just one single mode in colloidal in the two other direction, periodic direction, let's say, for the fluctuation. And so we deal with two quantities which are real and two other quantities which are complex. So I will not detail all equations which are here. What I want to focus on are more on the dynamics of the mean quantity, which a lot of here act for equilibrium, but they are tonally evolving. They are driven for the density by the turbulent flux, which is self-consistently computed from the dynamics of the perturbation here, and the flow, which are driven by the divergence of the Reynolds stress. And again, the Reynolds stress is self-consistent. You can see that there are two pieces here, which we will come on later on. A point which should be noticed, because we only retain one single mode, there's no mod-mod coupling so far. But with the work of Osgour and Pierre Guillon that you heard last week, then this is something that we can incorporate in the model by adding another mode. That's something we are thinking about. So the typical feature that you get from this model, for the density, for instance, so you have a particle source here. This is the radial direction here. We have a Dirichlet boundary condition for density here, and Neumann here. We impose a source. And if you wait long enough, then there will be a self-adjustment of the profile with the source, given a certain amount of turbulent transport and additional diffusive transport. So the mean profile will be that red line here, on which you will have on top turbulent fluctuations, which are quite small, as you can see. And what we scan is really those two C and G parameters. This is again in log scale, where in the bottom right you have the drift wave and stability, and the upper left the interchange, or Rayleigh-Bénard, with a few hundreds of simulations. Okay, so let's come to another important point, is that actually, if you would put what you could expect in terms of those fluid parameters for a tokamak, which is in Lausanne, in Switzerland, then this is practically the region that you would explore here, roughly. So one first result deals with the dynamics of the flow here, which is driven again by the divergence of the Reynolds stress. There's a viscous term here plus diffusion here, and friction and viscosity, and what was found in a gradient-driven regime, where you prescribe the gradient. So if you do not evolve the density, the equilibrium density, you freeze it, and you impose a given gradient, then this is what you see. When you decrease the C parameter, then you have a strong drop of the collapse, in a sense, of the zonal flow. This is the energy stored in the flow with respect to the total energy. But this transition here from no flow to almost dominated flow depends on the density gradient. And so if you increase the density gradient, you move from the green to the red. In the system that we are looking at, the gradient is not frozen. We impose a source. And when we scan this parameter, actually the mean gradient adapts to the source. And this is what you end up with. So each of these points is one of the simulation with the error bars measuring the dynamics of the turbulence on top of the mean. And what you can see that there's a collapse, but which is much smoother as compared to that one. So there's a reduction of the flow. So that was done without interchange stability. If we set G to 0, and then if you add interchange, then the picture changes even more dramatically. In the region where you expect interchange, then you go, if you increase the G parameter, then you go from a collapse to something which gradually increases here. So this means that interchange, even in this low C parameter, are able to drive flows in this case. Notice that, well, that's something I could comment on later. Then I told you that there are two leading terms for the Reynolds stress. There's a usual one involving the two components of the E-cross-B flow, but there's another one here coming from the pressure fluctuations here, that one. And we may wonder how they compete with each other or cooperate with each other and their relative weight. This is what is presented here. So I here is plotted the root mean square of the ratio of the two. And you can see that depending on whether you're dominated by drift wave here or interchange, then in interchange, the E cross P Reynolds stress here, the electric Reynolds stress dominates, while it's the opposite in the drift wave regime. And so, again, in this interchange dominated regime where the electric Reynolds stress dominates, we may wonder what's going on when we perform a scanning source and when we depart from the marginal stability. So this horizontal axis here stands for the departure from the critical gradient. In this case, this is the linear, the estimate, rough estimate of the linear critical gradient above which the instability pops up, normalized to itself. And so the farther you go right, the farther you are from the instability. And what you can see is first that the turbulent flux increases sharply when you exceed the linear threshold, which is called in our jargon a strong stiffness. So the system reacts extremely strongly to this departure. And when looking at the flows, there's seemed to be a reminiscence of what was seen in more advanced simulation, the fact that the flow tend to develop mostly close to the marginal stability. And actually, as we will see, those flows in the interchange regime tend to be structured as well. And this is what can be seen on this graph here. So you see the typical plot that we can get in the steady state regime. This is time, this is X, and what is presented here is mean flow. And you can see that there are zonal flows well localized spatially that are oscillating because of the interaction, the nonlinear interaction, but that stay almost steady. While if you are a very small G, so almost no interchange, then those flows do not exhibit this staircase-like structure. And so this can be measured by looking at the Fourier transform in the radial direction, which confirms what you can see just by eye. And in those layers here, they play the role, if you wish, of micro transport barriers. So the transport is reduced where the shear is large, and this is what can be seen here. This is the radius, dedicate a small region of this entire box here, where you can see on the left y-axis and in blue the shear of the mean flow, which oscillates here. And you see that whenever the shear is large, whatever the sign, the gradient or minus the gradient here, notice the scale here, which is always positive. So there's a maximum. So the gradient is maximum wherever the shear is large, whatever the sign. So an interesting point is to try to understand this interplay between those structures, those corrugations in the density gradient and in the flows. And so we performed a simulation where we started from a regime where the flows were there, and then we froze the gradient. We suppressed the back reaction of the turbulence on the mean density that was smoothed out. So we restarted with this constant in time density and rerun the simulation. And this is what comes out. So before 3 × 10⁴ here, the density equilibrium was self-evolving, self-consistently. And from that time on, we suppressed this dynamics here of the equilibrium, taking a smooth profile. And you can see that the staircases strongly, sharply, fast disappear. This is just a zoom here. So we still have the generation of zonal flows, but they are no longer structured. So it looks like the feedback loop, zonal flows, and corrugation on the equilibrium density is key. Something I should point out that we've been struggling in trying to extract some gradient relationship in those turbulence simulations, but there's no obvious feature that comes out either Fourier-like or by stability. Another, so once the staircase is formed, we may wonder what are the dynamics, and this is what we again did. We started from a steady simulation here. We stopped. We smoothed out completely the equilibrium, the flow profile, and let it further evolve. So this is the restart, no flow here, and then they reform actually with a slightly different pattern, but almost at least keeping the same characteristics. And when you look at the time evolution at a given position here to understand what's going on in this short time. This is a zoom here, and so we will be looking at the time evolution along this line where the flow here reforms, the staircase reforms. This is the flow time evolution in time here. So it's driven the flow by the Reynolds stress. In this case, there was no diamagnetic, so tau was equal to 0, no diamagnetic stress. So it increases exponentially, reminiscent of a secondary instability, as already pointed out. So this increases by due to the increase of the turbulence intensity, but also you can see that the phase plays some role at the onset here of the flow. And to disentangle, actually pi e is just the product of this turbulence intensity times this. And to disentangle the two, in the end, what matters for the flow is not so much the Reynolds stress, but the Reynolds force here. And so you can write the Reynolds force as follows, at least in log, when taking the log, you can really disentangle the effect of the phase and the effect of the intensity. And it turns out that actually the Reynolds force is completely driven by the curvature of the phase. It was already pointed out in a previous paper. Last point I would like to address is and this creates the link with the previous talk, actually, is the link with those flows and the avalanches. And in this case, well, when this is something I did not show. When we look at the turbulent flux, it can exhibit different features. And in some regime, it exhibits extremely long propagation events, long as compared to the order of magnitude of the correlation length of turbulence cells, and almost in an almost ballistic motion. So it's reminiscence of avalanche-like transport. And so those avalanches have different sizes depending on the parameter regime. In the case of drift waves, they are fairly short. You can have bursts. And so you recognize here on this plot the color blue and red, which correspond to the equilibrium flow, to the zonal flows. And in green here, this corresponds to burst of turbulence, taking above 2 or 3 sigma, so large bursts. And you can see on this zoom here that actually those bursts tend to perturb the flow here and disrupt it at some point. So there's some splitting, some transport of the flow by this burst. And conversely, in other regimes where the flow maybe are more steady, more well established, again, you can see in this case, it's more in the interchange preliminar regime where you can see long propagating avalanches events here. So now if you look at the time evolution of this flow here, this is presented here. So there's a zoom over there versus time. What you see are two things. In red, it's the turbulent flux. And in green or cyan, it's the zonal flows. You can see that the zonal flows, after some burst, decays exponentially. This is due to the friction coefficient that we put in. But more interestingly, actually, after some decay, when there's a burst of turbulence, then you can see that it reactivates the flow that then further decay. So can be regimes of perturbation or cooperation of avalanches and flows. Obviously, one of the questions here is the threshold for going from one to the other, and also whether it depends on turbulent regimes or on the strength of the flow themselves. Let me come to the conclusions. So, yeah, we investigated the tokamak edge turbulence by studying the dynamics of the flow and their interplay with the turbulence in drift wave and interchange turbulent regimes with the reduced model. What we found is that zonal flows are mostly active in interchange. I did not mention so much the adiabatic regime where the perturbation of the electric potential and density come together. They are radially structures, mostly in interchange regime, and the coupling to density profile is key. And this competition that we just discussed between avalanches and flow needs further investigation. What I presented, you can find it in the two papers, one already published, one recently accepted in Journal of Physics, Plasma Physics, and the PhD thesis of Olivier. And with this, I thank you for your attention.